Chapter 4, Lecture 3, Heat Conduction in Cylinders and Spheres. So let's begin our discussion by talking about cylinders. Here we have a cylinder that's at a certain temperature and it's radiating heat uh, through conduction uh, from the inside to the outside. Uh, and occurs in the radial direction. So it's not in the azimuthal or axial directions. In other words, it's only a function of r. It's not a function of theta and phi. So this is an approximation, but it's a rather good approximation, especially for long cylindrical pipes. And with a direct analogy, we'll extend this to spheres. The same kind of thing. It's only a function of r. Let's begin our discussion dealing with cylinders. Here we have a cylinder that has an inner radius of R1 and an outer radius of R2. The inner radius is at a temperature T1, the outer radius at a temperature T2, and the heat conductivity constant is K. So here we begin our analysis as before with the heat conduction equation. We can multiply through by dr and then integrate on both sides. And here we recognize the area for a cylinder is 2 pi r times L. So when we integrate this, it comes out to a very simple familiar formula. And again, we can put this in our Ohm's law kind of analysis by writing it in this form here, where Q dot is equal to the change in temperature divided by R of the cylinder. And R of the cylinder is given by this formula here. So this is our conduction resistance for a cylinder. So the exact same analogy we used before applies to cylinders. We can extend this to spheres in an obvious way. We can do exactly the same thing we did before, and we come up with the following equation. In this case, our conduction resistance is given by the following formula. So now let's say we have sort of a different situation where we have the inside of the cylinder or sphere is at a certain temperature. So the temperature is going to move toward the inner surface of the sphere or cylinder and then be conducted through the cylinder to the outside and then convected away from the cylinder or sphere. So here, again, this is exactly similar to what we did before. For the case of the cylinder, the total resistance is equal to the convection resistance from the center to the inner surface, our convection 1. Then we have the resistance of the cylinder, and then finally we have the resistance from the outer surface of the sphere or cylinder to the outside. So we can write this and sum these up as before. You can see the R values here. We copied over from the previous slide for the cylinder, and again for the sphere. So this is really kind of convenient. It's a very nice approach to solving these kinds of heat conduction problems in cylinders and spheres. So what happens if we have a multi-layer cylinder or sphere? So we have a sphere within a sphere within a sphere. Well, we extend this exact same analogy. We just consider these as resistors in series and go from the inside all the way through to the outside. Again, in a very natural kind of progression. So this is for a cylinder, but for a sphere, you'd have exactly the same kind of similar equation. So once we have determined the heat transfer rate Q, we can determine any intermediate temperature. Let's say we'll call it T sub J by applying the following relationship. So here, T sub I, we have to know T sub I, and T sub J is what we're trying to find. Q dot is going to be the same because it's the same all the way through all the layers. We just need to remember to sum up the resistances between the layer we know to the layer we're trying to find. So for example, if we know T infinity 1 and we're trying to find T1, this equation would look like the following, where we would have T infinity 1, which we know, minus T1, which we don't know, divided by the resistance between the two temperatures, which is this R conversion 1. So this assumes, of course, that we followed the previous slide and have found Q dot. We know R conversion 1, and we know T infinity 1. The only unknown is T1. Likewise, once we do that, we can kind of bootstrap our way through the process and we can find any other temperature. So, for example, once we find T1, we can use this same direct analogy and just go through and find T2, or we can go all the way from T infinity 1 to T infinity 2 by following this equation here. So T infinity 1 we know, T2 is what we're trying to find, and the denominator is just simply going to be the sum of R convection 1 plus R1. Q dot, remember, stays the same for all the way through the series layers. So let's take a look at an example from heat transfer to a spherical container. So here we have ice water inside of a spherical container, and it's a 3-meter internal diameter, a spherical tank made of 2 centimeter thickness stainless steel. So here you can see it's 2 centimeters thick. We're given the K value of the stainless steel. The ice is at T infinity 1 inside at the direct center, which is 0 degrees C. The tank is located in a room whose temperature T infinity 2 is 22 degrees C. The walls of the room are also at 22 degrees C. The outer surface of the tank is black, and so that's going to become important when we look at the radiation from the outer surface. And the heat transfer between the outer surface of the tank and the surroundings is by natural convection and radiation. So that's where we have to take both of these into account. The convection heat transfer coefficients at the inner and outer surfaces of the tank. So here on the inner surface and the outer surface are known to us. We want to determine the rate of heat transfer to the ice water in the tank and the amount of ice at 0 degrees C that melts in a 24-hour period. So what's happening here is that the heat from the outside is making its way to the inside and melting the ice. So to work the problem, let's take a look at the properties that we're given. So we're told that thermal conductivity is steel. We're given that value. We can look up the heat of fusion of water is given by this value. We're going to need this value to calculate how much of the ice is going to melt in a 24-hour period. Since the outer surface of the tank is black, the emissivity is 1. We're going to need to calculate the inner and outer surface areas of the sphere. So for the inner surface area, it's 4 pi times the radius, the inner radius squared. So we can calculate that value. We can calculate the outer surface area, the outer sphere. The heat transfer constant for radiation is the emissivity times the Stefan Boltzmann's constant, which we're given. We can look this value up. It's T2 squared plus T infinity 2 squared times T2 plus T infinity 2. So if you need to review this, look back at chapter 1 lecture. This is probably the last lecture in chapter 1 that talks about radiation. So if you go from from the inside to the outside here, you start at T infinity 1 at the center, and you go to the T1, which is right at this outer surface. You have your conductivity value we're going to calculate. Then you go through the sphere. That's R1, and then from the outside you actually have two values. You have the radiation value, and then you have the convection value. So, and these are in parallel. And then finally you get to the room temperature of the outside of 22 degrees C. Now, one thing we do not know, we do not know the outer surface temperature of the tank, T2. We weren't told that value. So one thing we're going to have to do is actually assume a value, and we're going to need that value here to calculate the radiation constant. So what value do we pick? Well, we know it's going to be closer to 0 degrees C than it is 22 degrees C. It's got to be somewhere between there. So our book picks a value of 5 degrees C, which is probably not a bad choice around that value. We know it's going to be closer to 0 degrees C than it is 22 degrees C. So what we're going to do is we're going to make this assumption, and then once we do our calculations, we can work our way back and calculate what the temperature is. And if it's close to 5 degrees C, well then we'll say it's a good assumption. If it's not, we'll have to assume a new value and then rework the problem and then check that. So now let's calculate our values. So again, we know the area, inner and outer surface areas. We know H1 and H2. We can calculate the H radiation, it's emissivity, Boltzmann Boltzmann's constant, and here's the temperatures that we know. We can calculate Ri, which is the convection 1. It's simply H1 times the area 1. We can calculate R1 of the sphere. So here we're inside the sphere, so it's 1.52 minus 1.50, 4 pi times K, which we were given, and times R1 times R2. We can calculate RO, which is the for the sphere. I'm sorry, we can calculate RO, which is 1 over H2 times A2. So here we're given H2, so we can calculate the value. We can calculate the radiation value, which is H rad times A2. So we can find the total R value by simply Ri and R1 are in series, and R rad and R0 are in parallel. So we can essentially form an equivalent resistance with these two guys here, and then add R1 and Ri and R1 to it. So when you add those numbers, you get a total resistance value of 0.00274 degrees C per watt. So having known that, we got our R value, we can calculate a Q dot. It's T infinity 2 minus T infinity 1. So T infinity 2 is our 22 degrees C. T infinity 1 is at our 0 degrees C. And our total is this value. So it turns out it's 8,029 watts. So now let's check our assumption that of the 5 degree assumption. So here, if we work our way back, we know what Q dot is. T infinity 2, we know what that value is. We don't know what T2 is, but we know what our equivalent is. So we can solve this for T2 and plug our values we know in, and we get 4 degrees C. Now that's pretty close to the 5 degree assumption, so therefore we don't have to go back and redo our calculations. But if this turned out to be 8 degrees C or 2 degrees C, that would indicate that we might want to go back and assume a different value for T2 and then work our way back and then do another check. So finally, to calculate the total heat transfer during a 24-hour period, we simply multiply Q dot times a delta T value, the time value. Well, there's 24 hours and 3,600 seconds in every hour. So in a full 24-hour period, the heat transfer that's going to go through here is given by 6,993 and 700 kilojoules. So how much ice would that melt? Well, we just divide by our heat of fusion value. And so the amount of ice we melt is 2,079 kilograms. So good luck working through these problems. These problems do take a little time because there's multi-steps involved. But slowly work your way through them and ask questions if needed.